Now let's take a look at standard free energy changes. This can be summarized using this equation here, similarly to what we saw with the change in entropy and quite a few chapters ago, the change in enthalpy. It's always going to be the sum of our products, in this case, Gibbs energy of formation times the stoichiometric coefficient for our product. So the sum of those minus the same for the reactants. So again, sum of reactants of delta G times their number of moles. So there's some conditions here specific to standard free energies. So if something's in standard state, we are able to assume that if it's a solid, that state of matter is solid, it's going to be a pure solid. If it's a liquid, it will be a pure liquid. If it's a gas, we also know that it will be at 1 atmospheric pressure specifically. And then if we have a solution, we know that the molarity, the concentration will be 1 molar. So these are all the standard state assumptions. And then there's one down here when we have the elemental state of something. The delta G of formation for that will be 0. So any element in standard state, and if we think about, say, iron, what is that in standard state? It's usually solid iron. That's going to be equal to 0. So if you want to think about the formation of iron from iron, requires no energy. You can maybe remember it easier that way. Similarly, O2 gas, that would be in its elemental state. That would have a Gibbs equal to 0. So these would be the delta G standard state formation values for some examples here. But again, anything in its standard state, so equivalent, carbon, etc., would have a delta G of 0. So let's take a look at this sample exercise 7 here. And it asks us to use Appendix C. So that's been provided on Blackboard, but you can also just Google any thermodynamic table, thermodynamics table, values, something like that. You could get these delta G's for, methane gas, CO2 gas, and H2O gas. And as I pointed out above, you may not find O2 gas because that is in its elemental state, and we assume that to be 0. So let me give us some values here from that table or from, any thermodynamic table. So for CO2, that's negative 394.4. And these values are all going to be in kilojoule per mole. So I'll just write it once here for CO2 gas. And then we have water vapor. So that's negative 228.6, again, kilojoules per mole, 0.402. And then we have methane, which is negative 50.8. And again, I would have looked up these values or found them on a table that I searched online. Now let's set this up to solve for delta G. And again, this is at 298. So these values were under those standard conditions. So let's do our sum of products times their coefficient. So I have 1 times CO2. So I'll just leave out the 1 and then we'll write negative 394.4 minus or plus rather, because these are both of my products over here. I'm going to have negative as well, 228.6. And we need to remember to multiply that by 2. All right, so these are both of our products, and then we're going to subtract, if you remember that equation, the sum of the reactants now. So methane is just going to be negative 50.8, but we will be subtracting that. So it's like we're adding that. This is our reactant, methane. And then I've left out the 0 times 2. But if you wanted to write it just to make sure that you knew that you did, you could make sure that you did include that rather. So let's multiply and then find the sum of these two values for our products. And then from that, you will technically add 50.8 because we're subtracting negative. So overall, we still end up with a negative 800.8 kilojoules for this process here. And if we wanted to comment whether or not this was spontaneous, it is a combustion of methane. So we could guess that we would end up with a negative value to show spontaneity, and we do. So let's take a look at this second sample exercise here, number 8. And we're asked here, or told here rather, for the combustion of propane at 298, so standard conditions. We're given this reaction here to show us the balanced relationship here, the molar relationship between propane and oxygen and carbon dioxide and water vapor. So we know these are the products of our combustion reaction. And without looking up any values, actually, we are just asked to kind of theorize or guess, do we expect delta G to be more negative or less negative than delta H? So we're trying to compare delta G naught to delta H naught here. So how can we do this without using any numeric values? Well, we are told that we have a combustion reaction. So we know that that will always be a negative delta H. And we want to say, okay, well, if delta G here is the sum of our enthalpy term minus our the difference rather of our enthalpy term and our entropy term. If this is negative and then we subtract, however we can approximate entropy change here, let's take a look at the moles of gas. So we have 7 moles of gas on the product side, but only 6 moles of gas on the reactant side. So since this is a larger number, we would expect an increase in entropy. And then if we just plug in a positive whatever value, and then we subtract that, we know that this negative value will get more negative. So delta G will be more negative than delta H if we just plug in some known conditions, being told that this is combustion and a exothermic process, and then we have an increase in entropy, so positive delta S.